Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. The search for alien life usually begins with stars much like our own, yellow, stable, and warm. We look for planets bathed in the familiar, life-giving light that powers Earth's green engines. But what if we broaden our horizon to the universe's cosmic failures, the brown dwarfs? These objects are too big to be planets, yet too small to sustain true nuclear fusion. They are the dim, cool, red embers of the galaxy, and they challenge everything we know about energy and life. The question is profound. Can life, specifically plant life, sustain a redshift garden under the perpetual twilight of a brown dwarf star? A brown dwarf emits a spectrum of light fundamentally different from our sun. Our star peaks in the visible yellow-green wavelengths, which is exactly where Chlorophyll-f, the pigment that makes Earth green, operates most efficiently. Brown dwarfs, however, are cool, often just a few hundred to a few thousand degrees Celsius. As objects cool, the light they emit shifts toward the red end of the spectrum and deep into the infrared, IR. This means a planet orbiting a brown dwarf would be bathed mostly in near-infrared radiation, near and invisible heat. This red-shifted environment poses two immediate and massive problems for photosynthesis: energy availability and thermal management. First, the energy problem. Photosynthesis is fundamentally a quantum mechanical process. Plants need photons carrying enough energy to kick-start the reaction that converts carbon dioxide and water into glucose. The further into the infrared we go, the lower the energy of the photons. Chlorophyll stops working around 700 nanometers. To survive under a brown dwarf, alien plants would need pigments capable of harvesting photons with wavelengths perhaps up to 1000 or even 1200 nanometers. Does such a pigment exist? On Earth, we have natural pioneers. Certain cyanobacteria living in deep, shaded habitats, like hot springs or under rocks, use Chlorophyll-f. This specialized pigment allows them to absorb light up to about 760 nanometers, a full 60 nanometers deeper into the infrared than standard plants. This demonstrates that life can adapt to harvest deeper red light. However, even Chlorophyll-f wouldn't be sufficient for a true brown dwarf orbit. We would need photosynthesis 2.0 pigments, perhaps utilizing metal clusters or highly specialized organic molecules, to capture the bulk of the dim near radiation. If these alien plants could evolve near-optimized pigments, what would they look like? They wouldn't be green. They might appear deep crimson, maroon, or even jet black, depending on their strategy. A black color maximizes absorption across all available wavelengths. However, this leads us directly to the second problem: thermal management. The brown dwarf is an IR radiator. While its light output might be dim for photosynthesis, its heat output, the long wavelength IR, is substantial. If a planet is close enough to the brown dwarf to receive adequate light for photosynthesis, the photosynthetic habitable zone, it might also be receiving dangerous levels of heat, potentially causing a thermal runaway. The alien flora would have to evolve incredibly sophisticated ways to discriminate between the useful near radiation, the fuel, and the detrimental long-wave IR radiation, the heat. They might employ highly reflective waxy cuticles or specialized structures designed to reflect the non-useful heat while allowing only the narrow, energy-rich bands of near light to penetrate the pigment layers. Imagine a plant with glossy, silver leaves designed to bounce away heat, featuring microscopic, dark patches optimized for absorption. Finally, consider the energy constraints. Brown dwarfs are dim. Even with perfect pigment efficiency, the light flux available might be extremely low. Life on a redshift garden planet would likely be slow. Photosynthesis might only occur for a few hours a day, or the organisms might require vast, thin collector surfaces. Think of forests of massive, umbrella-like leaves designed to maximize every photon capture. Their metabolism might be glacial, maximizing energy storage and minimizing waste, potentially leading to organisms that live for millennia. The possibility of photosynthesis under a brown dwarf remains theoretically open, but it demands an entirely new chemistry for collecting light and an elegant physical strategy for surviving the overwhelming infrared heat. It's a testament to the potential adaptability of life that even in the dimmest corners of the cosmos, the seeds of a garden might yet be found. For more incredible facts like this, don't forget to subscribe and turn on notifications.